How many of you have heard of 3D printing? Great, awesome. Well, for those of you who don't know, if there are any, 3D printing is a process in which you deposit material line by line and layer by layer until you reach your full part. As you can imagine, this is very versatile. Some of the applications are here. You can make personalized prosthetics. You can make very complex parts all at once instead of making small parts and then assembling them. And finally, engineers can now design parts that were never possible before, such as that on the far right. However, all of this comes with challenges. In industry, there are very high standards for what materials they're allowed to use, especially in matters that concern safety. Because 3D printing is so new, the quality control is not up to par. So it's very difficult to get a consistent material, and it's very hard to reproduce a good build. Also, 3D printing is very direction dependent. So if you build a part from left to right versus bottom to top, you can get drastically different properties. And why is that? To understand it, you have to go back to material science. One of the core ideas of material science is that this is a matter of cause and effect. The cause is the build process, or how you make the material. And the result is your material properties, such as strength, ductility, how it fractures, and so on. The link between them is the microstructure. Now, microstructure is just structure on a micro scale that makes up a material. So think of a bridge, right? The strength of a bridge is determined by the type of beams you have, the locations of the beams, and the orientations of the beams. It's the same thing for materials. When you have microstructure, it determines the material strength based on the type of microstructure, the location of the microstructure, and the orientation of the microstructure. And because it's a microstructure, you need specialized tools to see them. You can use a microscope, or if you're more high-tech, you can use X-rays. Because metals are so high density, you would want to use very high energy X-rays to see through the metal. Only way you can get high energy X-rays is through a particle accelerator. And luckily, we have a particle accelerator right outside of Chicago at Oregon National Labs. We do a lot of our experiments there. And with this technique, we can see 2D and 3D and even video images of microstructure. Here are some examples of microstructure. For one, you can see porosity, which are just defects or holes in your material. On one hand, if you have too many holes, your material is pretty weak. But you kind of want some holes because that will make your material lighter. On the other hand, you have crystal structures, which are the way that the atoms in your material is aligned. And this determines in which way your material is strong or weak. During the build process, the temperature and heat flow direction will influence your microstructure. If your laser is too weak, for example, you can get insufficient fusion between the layers and leave gaps, like what you see here on the screen. But if your laser is too strong, it can cause evaporation, and that will cause gas bubbles to form in your material. It's similar for crystal structures, but also more complicated because crystal structures can be any shape, size, or orientation. So now that we have the results, which is the microstructure, what about the cause? During the build process, in the process that we use, we have a powder nozzle and a laser. And at each point in the build, a computer is controlling various parameters related to these two things. Some of the things the computer is controlling are the powder material, the powder flow rate, the temperature of the laser, the width of the laser beam, and the tool path of the laser. And while all of this is happening, the substrate or material is giving off heat at the whole time. So this makes things very complicated. If we're to understand this chain of cause and effect, we need to isolate the effects of the parameters and their result on the microstructure. But if there's so many parameters and so many different ways a microstructure could turn out, how do we figure out that relationship or quantify that relationship? Sure, you can do thousands of experiments, but that'll take a lot of time and a lot of money. Instead, because I work in computational mechanics like Shiva, we use simulations. In the simulation, you see here, the red spot represents the heat of the laser, and it's building the material line by line, layer by layer, just like in a real build. After this, we can extract the temperature information and heat flow direction at every point in the build. In parallel, we can build the same exact part in real life and do experiments at Argonne on the microstructure. So we have microstructure at each point of the build in real life. Then, we can compare point by point and find the relationship between the temperature and the heat flow and their effect on the microstructure. The goal of this is to build this relationship between every link in this process. If we can build a good relationship between the process, structure, and property, we can go in the reverse direction. You can choose a material strength or property that you desire, backtrack and design the microstructure to help you achieve the goal, and then control the process parameters to get that microstructure. With this, we can get improved quality control in 3D printing and help it achieve its full potential. I'd like to thank our sponsors, and thank you for listening.